Welcome back. The objective of this video is to algebraically find the equation of the inverse of a function. So we'll go through how to find that algebraically, and we'll also do some extra practice at graphing inverse functions. So the process for algebraically finding the inverse of a function is listed here. The first step is to interchange x and y in the formula. So we'll flip our x's and y's, as we know that's what we do for an inverse function. And then we'll resolve our new function for our new y. So we'll solve for y to get the formula for the inverse. And then we'll state any restrictions on the domain of the inverse. First, though, before we even start, I kind of skipped that. Determine that an inverse will exist. That is, check to see if it's 1-to-1. And then in step 3, the final step is just to put it back in function notation. So your y now would become f inverse of x in the equation. Now, I do have some students in the past that have done this, and they prefer just to solve the equation for x to begin with. So they get some version of like x equals, and then they say, okay, well, this is really the f inverse of x, and then they flip their x's and y's then, and they take the y that's over here and then make that x. So they flip the x's and y's second. They essentially do step 1 as step 3. And we'll get some practice on that in just a minute. So in example 4, for each of the following functions, sketch the function and y equals x, state the domain and range, find the inverse, state the domain and range, sketch the inverse, and verify that they are inverses algebraically. So let's take a look at what we've got here. So our first function, f of x, equals the square root of x plus 3 minus 2. So our original function here, our parent function, is a square root function, which just looks like that. So this is going to pass the horizontal line test. This is going to be 1-to-1. In fact, this function has just been shifted left 3 units and down 2 units, which I have here in blue. So the graph of our original function, we shifted 3 left and down 2, and I have plotted those points, and there is a graph of f of x equals x plus 3 minus 2. Our domain for this function is, well, the x's based on our graph we can see here goes from -3 to infinity. And our range for this function, we don't have any y's below -2, but from -2, and that's going to be inclusive as well, to infinity. So let's go ahead and algebraically find the inverse of this function. So our function here is y equals the square root of x plus 3 minus 2. And we'll go ahead and flip our x's and y's. So now this is x equals the square root of y plus 3 minus 2. That minus 2 is on the outside. I made a big square root there. And let's go ahead and solve for y. So we add 2 to both sides, and we get x plus 2 equals the square root of y plus 3. And then we square both sides. So show all this work, and we get x plus 2 quantity squared equals y plus 3, and the square root of x plus 2 squared minus 3 equals y. So that's our inverse function. So f inverse of x equals x plus 2 squared minus 3. Now this is a parabola that's shifted 2 units to the left and 3 units down. But we can't graph the whole parabola here, because our original function has got restrictions on it. So we're only going to graph the what would be our positive x's. So our domain on our inverse function is going to go from -2 to infinity, and our range is going to go from -3 with a bracket to infinity. So flipping my x's and y coordinates, I'm only going to graph, if you will, the right-hand half of this parabola. And so that's our restrictions on our domain and our range. And you can see here, graphing across y equals x, it is indeed symmetrical. So if I graph the whole parabola, it wouldn't be 1-to-1. It wouldn't pass our horizontal line test. And plus, we wouldn't have symmetrical points with the points that we graphed originally. Example B, we've got g of x equals the cube root of x plus 2 minus 1. A cube root function, we don't have any restrictions on our domain and range. So in our original function, our domain is all real numbers, -infinity to infinity, and our range is also all real numbers, -infinity to infinity. Let's take a look at this algebraically. I do like to do this first. So our function here, y equals the cube root of x plus 2 minus 1. I'll go ahead and I'll do this the other way. I'll do this the student way, where they solve for x first and then flip the sign. So we add 1 to both sides right away. We get y plus 1 equals the cube root of x plus 2. Then we'll go ahead and cube both sides, and we get y plus 1 quantity cubed equals x plus 2, and y plus 1 cubed minus 2 equals x. So x is my new y. So the inverse of x equals the quantity x. Now our y became x plus 1 cubed minus 2. So there's our inverse function. And now we'll go ahead and graph our original function. Our original function, the cube root of x plus 2 minus 1. I've done a little bit of a table of values here, and that function is going to look something like that. So that's our original. And then our inverse function is a cubic function that's shifted 1 unit left and down 2. So 1 unit to the left and down 2. So this is kind of our new 0. And that function is going to look something like that. So here's f inverse, our inverse of x, and then the blue one is f of x, and the domain of that is all real numbers, -infinity to infinity, and our range is also -infinity to infinity. So there are a couple examples of graphing a function and its inverse, and also finding the inverse of the function algebraically. And you'll get some more practice with this when I see you in class.